Okay, just one thing before you start with this numerical, just some basic revision points. Let us discuss it. And I write it back. See, when we're talking about current electricity, the study of electric charges in motion is called current electricity. I'll be starting with the revision of current electricity and EM waves. These two chapters I'll be completing today, and tomorrow AC and EMI. So your first book will be completely over, and from the second book only few things are left, like wave optics has also been covered. Book is almost done, that we'll see. So when we are talking about current electricity, the study of electric charges in motion is called current electricity. So firstly, you should be aware of the term current electricity. Then what all things we have in this lesson? We have the first basic term, that is the electric current. Electric current is charge by time, Q by T, and the SI unit is amperes, right? Then when we're talking about the electric current, you should be aware of the fact that electric current is a scalar quantity. This is an important point to be discussed. One more thing you have when we talk about the electric current, there are conventional currents and there are electronic currents as well. Because we'll be doing EM waves, that's why I'm relating it with this. Because there is the concept of this displacement current and all. So there has to be a conventional current and an electronic current. So direction of motion of positive charges is taken as to be conventional current. When we are talking about conventional current, this means direction of positive charges. This is taken as to be the conventional current. All right. Then we have the electronic current. Electronic current is taken from the negative charges. So electronic current, because electrons are negatively charged, so direction of electronic current is opposite to that of conventional current. So exactly it's opposite. That is the direction of negative charges are taken. So electric current is a scalar quantity. Other thing in current electricity, which is a good and important quantity to be remembered, is EMF, electromotive force. EMF of a source is defined as the work done by a source in taking a unit positive charge from its lower potential value to its higher potential value. This is the lower, this is the higher potential value, right? So it's the energy supplied by the source in taking unit power. So this basically is work done by charge. That's why we have this quantity which is known as voltage. SI unit is volt. So voltage's formula is also W by Q. All right, then you have Ohm's law. What is Ohm's law? Ohm's law is important in this lesson. It can come as a 2 marker or as a 3 marker to plot the graph as well. So when a question comes from Ohm's law, mention that current flowing through a conductor is directly proportional to the potential difference across its end, provided two conditions I told you, temperature, pressure, these things should be unchanged. So V is directly proportional to I, where your constant is R. So V is equal to IR becomes your Ohm's law. This is very important, class. Then the resistance is the opposition to the flow of the charges, right? The conductor is able to oppose the flow of charges. This quantity is known as resistance. So how do we write it? Resistance is actually the ratio of voltage and current, and its individual formula, because it depends upon length and it is inversely proportional to area. So we have this formula also, resistance is equal to rho L by A, correct? Now see, inverse of resistance, you have the concept of resistivity. Just opposite to it, resistivity is this rho, that is RA by L. SI unit will be ohm meter because its SI unit is ohm. Then we have the concept of current density. Current density is represented by the unit vector J. Current density is basically amount of current per unit area. We have also one more formula for current, that is J dot A, or you can write it as JA cos theta. Clear? Then if you remember, four terms we discussed: conductivity, conductance, mobility. Remember, we have seen these terms. So conductance is just, when we're talking about conductance, it is just inverse of resistance. And when we're talking about conductivity, this is just inverse of reciprocal of resistivity. These terms we have with us. Then yes, one more thing, resistivity is of different materials are different. So it's a material dependent property. Then what all things we discussed? One more thing, very important term I forgot: drift velocity. Drift velocity we have seen. So it's the average velocity that is acquired by the free electrons of conductor in the opposite direction of the externally applied electric field. That is known as the drift velocity. So we have the formula of drift velocity, Vd. Drift velocity is formula. This is E capital E tau by M. Yes. And from this, using this, we have one more formula for resistance, that is ml by ne square tau a. For resistivity, we have the formula m by n e square tau. This was resistivity. Also, where all formulas we had where drift velocity was used, current is equal to NEA VD. This relation was also there. If we're talking about current, we have to talk about current density as well. That is NEVD only, because area will be cancelled, current per unit area. So these are the formulas in your lesson where drift velocity has been mentioned, right? Other form of Ohm's law we have, that question also comes in the exam. V is equal to IR we have discussed. Other questions also. Other form of Ohm's law is expressed as J is equal to sigma E. This basically means this is the current density and electric field. This is the current density J. This is the electric field, right? And what is this? This is the conductivity. This is a relation between them. So basically, this tells you that Ohm's law, when the resistivity of material does not depend on the magnitude and direction of the applied electric field, that's where you have this formula. Then one more formula we had seen, where we had seen the temperature differences changes. So temperature coefficient of resistance, alpha, is very important in your lesson. Alpha, separate formula. This formula also I'll suggest you, if you remember, R2 minus R1 by R1 into T2 minus T1. This also because separate questions have been asked. So it is defined as the change in the resistance per degree rise in temperature. Per unit original resistance per degree rise in temperature. So this is how it is given. And you have the main formula also. R temperature is equal to R naught 1 plus alpha delta T, whatever is the temperature change. And what is the effect of this? Effect of temperature on resistance and resistivity. This is also very important for your board exams. The graphs can be asked, separate formula can be asked, values can be given to you, and then the interpretation of these values can be asked. You should remember three things in this. First is the case of metals. Remember it like this. Second is the case of semiconductors and insulators. Semiconductors plus insulators both. And third is the case of alloys. So even if in your final exam something comes, you have to mention it like this. Also, one more thing, class, everybody has the notes written, right? Everybody have notes with you. So what you all do, if any point you want me to stop, where you want to copy down or you want to note down anything, or you want me to repeat, just stop me in between. I'll just wait for you to write down, because I'm just scrolling it directly while writing. So it can happen that you want to copy down something. So just let me know, scroll up, scroll down. I'll just wait before proceeding further. All right. So yeah, I was discussing effect of temperature on resistance. So how to remember for metals? Remember it like this. Metal separately, that for metals, alpha is positive, right? So it means temperature increases, resistance increases. Come to semiconductors and insulators. For these, alpha is negative. That means temperature will be increasing, but your resistance will be decreasing. Alloys. Specifically, one more thing I'll tell you, in your exam, in your board exams, question can come not by directly using the term alloy. You can be asked to write about Constantin. Or one more thing that I have seen a lot in the exam is mangan. It can be asked, these two names are mentioned, and the interpretation or effect of temperature can be asked to you in your exam. So you have to write, you have to understand that both of these are alloys. And alpha is very small for alloys. It's very small. All right, that's why they are used as standards for making the resistors. The rest of the graphs which we have seen, definitely that you have to do. But these are the basics. Yeah, one more thing that we had seen in the class, which we discussed, was the mobility of charge carrier. That can be asked in your MCQs, 1 markers or 2 markers, not more than that. Mobility of a charge carrier. So mobility, how do we write it? Drift velocity per unit electric field. Or this can be written as Q tau by M. This is also helpful. If anywhere this is asked, this can be used, please write it. This will be helpful for you. One more thing. If this can sometimes be linked to your semiconductors lesson. Mu, this is the mobility of a charge carrier. Okay, do one thing. Do not write down anything. I'll slowly scroll it down. So wherever something important is there, you can stop me. Let me just discuss the theory part. Because I think some things you should write in between. That I'll tell you. So this is mobility of a charge carrier. Now, this can be related to your semiconductors. How? It can be related by, they can give you the average relaxation time of electrons. They can mention electrons, and they can give you the mass of electron you have to take by yourself, and the charge of electron you have to take by yourself. So mobility of charge carriers, which charge? Electron. Mobility for electron will become E tau E by Me. And one more thing, holes. Holes. So here you have tau H, you have mass of the hole, and you have the electronic charge. Electronic charge will be the same. Do not be confused that which value we have to write, because it's the deficiency of electrons only that create holes, right? So if a question is tough, if the question is relating your current electricity chapter with your semiconductors, this can be written. So then further you can write electronic charge will be the same. Whatever is the relaxation time and mass mentioned, you have to write it. But mass of hole also, that will be the mass of electron. This you can copy it down later. I'll give you time for this because this is important. Then there is one relation between electric current and mobility. Relation between electric current and mobility. So this also you have to remember in 2 phases. Learn this also in 2 phases. That will be helpful for you. For conductors separately, why am I emphasizing on this so much is because you have a chapter named semiconductors in your lesson already. So examiners have tendency to relate the questions and make interlinks for the chapters, like current electricity with EM waves questions and semiconductors, especially these can be asked. So that's why I'm saying conductors and semiconductors learn it in this way in current electricity itself, because for semiconductors it can be asked separately. So second is semiconductors. So for conductors and semiconductors, separately remember the formula. For conductors, current is equal to electronic charge, number density, area, mobility of electron into electric field. For semiconductors, these three things can be taken common. They have to be written separately. Number of electrons into the mobility of electrons plus the mobility of holes into the number of holes. This is number density of electrons. This is number density of holes. If needed, you can. Then you have the concept of ohmic and non-ohmic conductors. One more question can be asked in the exam to differentiate between ohmic and non-ohmic conductors. All right. So for ohmic conductors, what all things you have to remember whenever the question, if the question comes to differentiate between them or to write about it. So you have to remember which obeys the Ohm's law. These are called ohmic conductors. Apart from this, VI graph is a straight line. These 2 points are very important. VI graph is a straight line. All right, VI graph is a straight line. And best example for ohmic conductors are metallic conductors. Example also you can mention in the exam. Metallic conductors. Then for non-ohmic, all these points will be different. Firstly, VI relationship will be non-linear. Here in this case, this becomes non-linear. This does not obey Ohm's law. Also, VI graph does not pass through the origin. This does not pass through origin for the non-ohmic one. These things you have to remember. All right. Superconductivity, I have told you that a critical temperature is important, required. So that you can leave for the board exam. That's not very important. Then comes resistors in series, resistors in parallel. For series, equivalent resistance will be directly the sum R1 plus R2 plus R3. For parallel connection, 1 by R equivalent will be 1 by R1 plus 1 by R2 up till so on. These things you have to remember. For division of current, this you can use in your exam for division of current in resistors if they are joined in parallel. See, division of current joined in parallel. If they are joined in parallel and you want to find out the current in one particular branch, suppose in this branch I want to find out. So for first current, this will be R2 by R1 plus R2 into the total current. For the second current I2, this will be R1 by R1 plus R2 into the main current I. This also you can use, it is helpful. Then comes those concept, internal resistance and all. Internal resistance, EMF, terminal potential difference, all these points. So there not much changes are there. In these formula you have to remember E is equal to V plus IR. This is very important. And V is equal to E minus IR. The relationship between all these three. There nothing is important, but just remember one thing: whenever the potential difference of a cell, when it is charged, V is usually greater than E when cell is charged. If in your MCQs this question is asked, you can attempt it. Then cells in parallel, cells in series and mixed grouping, that also we discussed. NE by R plus NR for this was for series. This is for cells. So this was for in series. Then we had seen ME by MR plus small r. This was in parallel. Then one more thing we had seen, mixed grouping. M and E by MR plus NR. This was mixed, right? Then heating effect, questions can be asked on heating effect also. So what all things you have to remember in heating effect? The main formula, basic formula you have to remember, that is VIT. This is the formula for VIT, or I square RT. H is equal to I square RT is the main formula which is used. And this is only known as Joule's law of heating. So if you encounter this term, Joule's law of heating, and in the exam if it comes Joule's law of heating, so this is not out of syllabus. This basically says that heat is directly proportional to square of the current. It is directly proportional to resistance, inversely proportional to potential, and all like this. Exactly this term you have to explain. Then power also can be related. Power is V square by R. P is equal to VI. That can be interchanged and converted. SI unit of power, remember, that is watt, right? All these things you have to remember. One more thing in power, if appliances are given to you, lots of powers you have calculated and different appliances are there. So if for power you have to find out the series and parallel combination. Suppose devices are connected in series and parallel, then how will you find out the net power? So for series, this is like capacitor. For series, the equivalent power will be 1 by P1 plus 1 by P2, like this. And for parallel combination, power will be P1 plus P2 plus P3 and so on. Last thing, maximum power theorem you should remember. Maximum power theorem. Maximum power theorem. Maximum power theorem basically says that output power of a source of EMF is maximum when the external resistance of the circuit is equal to the internal resistance, and the formula of the maximum power is E square by 4 into small r. This can be asked. And one more thing, efficiency can be output power by the input power. This is how the efficiency can be asked. Then Kirchhoff's law, that you can handle. Potentiometer, Wheatstone bridge were deleted. So meter bridge is also deleted. That's it. So I'm just scrolling it. Wherever you feel like stopping, just stop. Otherwise, we'll continue with the numericals. See, this says that two wires XY have the same resistivity. Look, resistivity is same. Cross-sectional areas are different. So what is the ratio of the cross-sectional areas? 2:3. And ratio of the lengths, 1:2. So length, area, resistivity. Firstly, they are connected in series, then in parallel. Firstly, the connection is in series and then in parallel to a DC source. Find out the ratio of drift speed. Drift velocity you have to find of the electrons in the two wires for the two cases. Look, when we're talking about the series, in series, which quantity is constant? The current is constant. So drift velocity is inversely proportional to the area. So directly, let's say these were x and y. So drift velocity for x by drift velocity for y. This will be inverse. So area of y will come up by area of x. Simply that is 3:2. The ratio will be inverse 3:2. Clear? Answer is very easy for the first. Come to the second part. That is the parallel connection. The parallel connection. Look, for parallel connection, potential which is equal to IR. This potential is constant in parallel connection. Current is different, right? Current varies. So how does current vary? Current is inversely proportional to the resistance. And you know resistance is further inversely proportional to the area. So what can we conclude about the current? Also one more thing, not just area, it is directly proportional to length also, length by area. So we can conclude the fact that current is inversely proportional to area by length. Understood this? See, I am repeating. Current is inversely proportional to resistance. So whatever will be the value of resistance, it will be opposite for current. Resistance is L by A. So current is proportional to A by L because this is reciprocal of it. Right? This relation is helpful. Remember it for other numericals also. It's important. Now, what all things are given in the question? Let's put it directly. So current for X by current for Y. This is area of X by length of X. This is length of Y by area of Y. So this ratio, areas ratio will be 2/3 and lengths ratio is 1:2. So 2/1. This becomes 4/3. But this is the ratio of current only. Why have we calculated current? Because current is different in parallel combination. In the previous part, in series, current was constant. So we could easily find the question and the answer could come in one line. But now when we're talking about the parallel connection, in parallel connection, current is different. So in order to find out drift velocity, we have a relationship between current and drift velocity, that is NEAVD. So for X also, this will be NE, area of X by drift velocity of X divided by Y. NEAY, drift velocity of Y. NE will be cancelled. Areas ratio is 2/3. Drift velocities ratio, we have to calculate VDX by VDY. So one more thing, class. Current we have calculated. Area we know. Cannot we calculate VD, drift velocity? Can't be calculated. So drift velocity of X by drift velocity of Y. This is 2/1, which is equal to 2:1. So answer is the same. No, it's different. This was 3:2. This is 2:1. Write it. See, this says a uniform wire is cut into 10 segments, increasing in length. Length is increasing here in equal steps. The resistance of the shortest segment, this is R, and the resistances of other segments increase in step of 8. Means you have to keep on adding 8 into it. If the resistance of the longest segment is 2R, find the value of resistance and find the resistance of the original wire. Look how you have to solve this question. Resistance of the first or shortest segment. This is given as R ohms, right class? Now resistance of the second segment. What it saying in step of 8 means R plus 8, right? Then third segment. Also this is saying 2R, no? No, that is the longest one. A uniform wire is cut into 10 segments, increasing in length in equal steps. Resistance of the shortest segment is R, and the resistances of other segments increase in the steps of 8. That is first one. Then third segment, R plus 8 into 2, like this, right? Second, for 2 more resistors. So similarly, even if you talk about the 10th one, R plus 8 into 9. This is like a general formula that we have, which is equal to R plus 72. Right? Now look, longest segment. This is the longest segment. Longest value of the resistance, longest segment is given to as 2R. This means 2R is equal to R plus 72. So from here, resistance is equal to 72 ohms. Then resistance of the original wire. All these are connected in series. So for the equivalent resistance of the original wire, 1R, then R plus 8 plus R plus 16 second R2 plus R plus, like this you have to keep on adding till R plus 72. So 8 you have, 16 you have, 32 you have, like this you have to expand it. So one thing for sure, that is 10R will be there, R plus R, because these total were 10, total segments were 10, 10R is there. And if you take 8 common, then 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 will be there. 5, 6, 7, 8, 9. So this is 45. 10R plus 8 into 45. R's value, you know, it's 72. So 10 into 72 plus 8 into 45. This is the answer. That will come out to be 1080. It's a different question. Write it down. Some more different questions. Let's see. Calculate the temperature at which resistance of a conductor becomes 20% more than its resistance at 27 degrees Celsius. The value of temperature coefficient of conductor is 2 into 10 to the power minus 4. What is this? This is the value of alpha given. Look, uh, this says resistance of the second one is 20% more than the first one. That is 20% of R1 more than R1. So R2 will be equal to 1.2 R1. Temperature 1 is 27 degrees Celsius. This is 300 Kelvin. And alpha is given as 2 into 10 to the power minus 4 per Kelvin. This you can now solve further. So T2 minus T1 is equal to R2 minus R1 by R1 alpha. So R2 and R1, this relation we have written. So R2 will be 1.2 R1 minus R1 by R1 into 2 into 10 to the power minus 4. So R1 will be cancelled from everywhere. And this will be equal to 1000 directly. Also, T2 is equal to 1000 plus temperature first, and first temperature was 300 Kelvin. So this becomes 1000 plus 300, that is 1300 Kelvin, or you can write it as 1027 degrees Celsius. Noted? Two cells of EMF, 1 volt and 2 volt, and internal resistance is 2 ohms and 1 ohm. So this is E1, E2, R1, R2 connected in series and parallel. First part, second part. External resistance we have to find out in the circuit so that current through the resistance be the same in the two cases, in which case more heat is generated in the series. See, current in the series, this is given by E1 plus E2. Total EMFs you have to add, and internal resistances, all the resistances you just have to add with the external resistor. So this is 1 plus 2, that is 3, by this is also 2 plus 1, that is 3. This R is unknown, let it be R. Fine, till here it's clear. When they are connected in parallel, so E equivalent is E1 R2 plus E2 R1 divided by R1 plus R2. This is the formula. So this is 1 into 1 plus 2 into 2 by 1 plus 2. This is 4 plus 1, 5 by 3. This is current, this is EMF, and then internal resistance. What will be the internal resistance? R1 into R2 by R1 plus R2. So this is equal to 1 into 2 by 1 plus 2, which is equal to 2 by 3. If they are connected, if the current is connected in parallel, then E equivalent by R equivalent plus the external resistor, capital R. So everything we have calculated. This is 5 by 3. This is 2 by 3. And this is unknown, that is R. This is equal to 5 by 2 plus 3R. Now look, in this question, this is telling you that the current in the two cases is same, parallel and series. So you can equate this 5 by 2 plus 3R equal to 3 by 3 plus R. Now it's just a linear equation with one variable. Capital R is our variable. So this is 15 plus 5R is equal to, this is 6 plus 9R. So this is equal to 4R. 4R is equal to 9, right? So R is equal to 9 by 4, which is equal to 2.25 ohms. This is the answer. Noted?